everybody, wherever you're joining from. And I'm pleased to welcome you to our Zoom participants and our social media viewers to this, the first binational conference on the intersection of climate change and water, agriculture, and economics, UK-Mexico conversation to increase bilateral cooperation. We are really happy to be here today in this effort to bring our communities together in this important conversation. My name is Jorge Velázquez from Mexican Institute of Water Technology, and I'm honored to be your host today. Today, we'll be joining a series of conversation from specialists both from Mexico and the UK to tackle these important topics. Today, more than ever, we must join efforts if we want to fight against global warming, and today is all about that. It is about community. It is also about sharing knowledge. We're all in this together. In this opening season, we're going to hear from a high-level personality from both countries on this matter. But before starting with you and to pass the mic to our distinguished guests, I would like to share with you the dynamics that we're going to follow in this event. As you can see, all the microphones are muted, and they will stay that way for everybody to have a better experience. If you need to do any interaction with the participants or the speakers, this will be through the chat with the Zoom application, and for our social media live attendees, it will be done through the comment section. This seminar is being recorded and will be uploaded to the social media, both from the Institute and the Embassy of Mexico in the UK. Without further ado, let me introduce you to our first speaker, Her Excellency Madam Josefa Gonzalez Blanco Ortiz Mena. She is Ambassador of Mexico to the United Kingdom of the Great Britain and the Northern Ireland. She also serves as Mexico's permanent representative to international organizations based in London, such as the International Maritime Organization. She has an extensive experience in Mexico public service, international cooperation, and teaching. She is former Cabinet Secretary of the Environment and Natural Resources of Mexico, and for over a decade, she had led conservation programs, including species reintroduction and reforestation, promoting ecosystems recovery and sustainable development in Chiapas, Mexico. Madam Ambassador, welcome.
Thank you very much, Jorge. It is an absolute pleasure to see you. And muy buenos días a todas, a todes que nos acompañan hoy. I'd like to welcome our dearest panelist, the Undersecretary of Multilateral Affairs of the Mexican Ministry of Foreign Affairs, Marta Delgado, our Deputy Director of Risk Assessment and Investment, Flood and Coastal Risk Management, Jonathan Day, Head of Mexican Institute of Water and Technology, Adrian Pedroso, Head of the Mexican National Commission of Water, Germán Martínez. Welcome, everybody. Bienvenidos y muchas gracias. Welcome to this first binational conference, UK-Mexico, on the intersection of climate change and water, agriculture, and economics. It is an honor to speak before you today on such a relevant and important topic surrounding the countries of the world today. Como embajadora de México en el Reino Unido, me da un gran gusto poder reunirme con ustedes para dialogar sobre la intersección entre el cambio climático, el agua y las formas en que podemos ampliar la cooperación en esta materia. Today, the world faces a double threat of an ongoing COVID-19 pandemic and global warming, while less developed countries have been disproportionately affected by both of these circumstances. Challenges in the global north, such as unprecedented forest fires and flash floods, or the prevalence of high infections and transmissions regardless of national vaccination efforts, expose shared vulnerability with the rest of the planet. In this context, international cooperation has again provided its value as a crucial strategy to tackle common challenges, whether they are remaining within the 1.5 degrees increase limit in temperature as part of the global action negotiation, or fostering partnership to guarantee that vaccines and treatments are accessible for those who are in most need. México y el Reino Unido son socios estratégicos en lo económico, político y cultural. Y hoy también reafirmamos otro ámbito en el que también somos socios estratégicos, el ambiental y el de la lucha contra el cambio climático. COP26 brought us together to assess and understand our shared experience with climate change and water. It also brought us together to learn from each other and work towards to diminish the effects of climate change. Building on collaborative work, the Embassy of Mexico in the United Kingdom and the Mexican Institute of Water Technology, and IMTA, have organized jointly this binational conference, aiming to find contributions to the debate on best practices to solve common problems around the extreme meteorological phenomena caused by climate change and the potential impact on water and food security. El manejo sustentable del agua es una pieza clave para el futuro de nuestras naciones, tanto individual como colectivamente. El agua es el elemento esencial para la existencia de cada ser humano y, a su vez, es un factor económico primordial para el desarrollo de nuestros países. Droughts, floods and water contamination have become more prevalent around the world each year. Water security is an issue all countries are facing, and collaboration between countries is of the utmost importance. In this context, I'd like to mention that as part of my tenure in the United Kingdom, I've seen first-handed the potential of learning from each other. I witnessed last week the construction work taking place along River Thames, one of London's most astonishing projects regarding water management and supporting the capital's resilience against the effects of climate change. Ahora bien, nuestra nación no se ha quedado atrás en la lucha contra el cambio climático. En el 2012, México fue el primer país en adoptar una legislación climática. Además, durante los últimos 25 años, México ha sido una pieza clave en la lucha internacional contra el cambio climático, ayudando a avanzar las negociaciones internacionales. Reiterando que históricamente el Reino Unido y México han logrado mantener una fructífera relación bilateral, hoy nuestros países comparten más que nunca la importancia y la responsabilidad de luchar contra el cambio climático y luchar por el acceso a agua limpia en forma democrática, justa y equitativa. Por medio del importante diálogo bilateral entre México y el Reino Unido, nuestros estados crecen en sus iniciativas, conocimientos para combatir el cambio climático. In the context of this binational academic conference, we acknowledge and welcome all participants, institutions, including the University of Exeter, University of Bristol, University of Manchester, UNEP Financial Initiative, Center for Atmospheric Science at the National Autonomous University of Mexico, the Imperial College of London, Institute of Ecosystem and Sustainability Research, UNAM, University of Birmingham, University College of London, Institute of Geography, UNAM, Sonora Institute of Technology, University of Glasgow, and Cardiff University. For the roundtable two-day session, over 20 scientists and experts from top higher education institutions and research centers will provide insight and recent research and best practices on 5 areas: climate finance, economic of climate change impact on water resources, water, energy, food system, and ecosystemic responses to water extremes. Through your active participation, we are looking forward to sharing experience and knowledge between Mexico, a country with a huge potential to develop green solutions, and the United Kingdom, a pioneer country in climate action commitments and strategic global partner. Adrian Pedroso, muchísimas gracias por tu gran participación, por tu gran entusiasmo, por tu gran trabajo en la creación de este foro. Muchísimas gracias. Querido Germán, gracias a ti también por facilitar, por apoyar y por estar co-creando este gran evento. Thank you very much. Muchísimas gracias. And I wish the best for this forum. Thank you very much.
Thank you very much, Madam Ambassador. Now let me introduce to our next speaker, Madam Marta Delgado Peralta. She is Undersecretary for Multilateral Affairs and Human Rights at the Mexican Ministry of Foreign Affairs. She was elected to local Congress in 2003. From 2006 and 2012, she served as Minister of the Environment of Mexico City. During her time as Mexico City's local secretary, she helped to develop environmental policies, including Green Plan of Mexico City, the Climate Action Program, and the bike sharing program that we love called EcoBici. Thank you to be here, Undersecretary. The mic is yours.
On the contrary, thank you, Jorge, and distinguished colleagues. Thank you for the kind invitation to participate in this conference. It is an honor to me to share this space with you. Germán Martínez Santoyo, General Director of the Water National Commission, and our colleagues from Agua, my dear Ambassador Josefa Gonzalez, and Adrian Pedroso, Head of Mexican Institute of Water Technology, and Jonathan Day from the Food and Coastal Risk Management Agency. I want to say that this is a splendid occasion to talk about water today. My expectations for these events are that the result is useful for the scientific community in Mexico and also in the UK. So that is correspondent research work can be strengthened and thus have a robust contribution to design an application of policies for a sustainable development. After the COP26, we identified the need to increase our work oriented to the enhancement of the climate action, especially if we are aiming to achieve the Glasgow Climate Pact, which is one of the outcomes of the Conference of the Parties. The last can only be turned into reality if the collaboration amongst different governments and civil society, the academia, the youth, and the private sector is also strengthened. So climate change, biodiversity loss, and land degradation will bring new pandemics with deeper impacts in the future. Hence, it is imperative not only to increase financial resources to this issue, but more importantly, to make climate-smart investments and to use those funds effectively and efficiently. Therefore, we see the need of strengthening the link between the 3 Rio Convention's agendas, the desertification, the climate change, the biodiversity, in order to optimize the resources while addressing the common environmental challenges. These agendas are interconnected, since climate change is an accelerator of a loss of biodiversity. It has an impact on the increase in desertification. In turn, this conservation of biodiversity supports the restoration of ecosystems and soil recovery, while these joint actions contribute to the sequestration of carbon dioxide. So it is very important for us, for Mexico, to link the three conventions in the future negotiations. We are promoting the creation of projects and synergies between the aforementioned challenges and the nature-based solutions focusing on ecosystem-based approach. Also, we have to keep the Sustainable Development Goals as core principles of the whole negotiation processes. Climate change, desertification, and loss of biodiversity are not just environmental problems, yet they are also social issues, and we as governments must face them with a transversal view, incorporating gender and human rights perspective in our actions and policies. Therefore, I invite you to include these perspectives, these elements in every research that you develop now and in the future. For example, Mexico, we aim to promote sustainable agri-silvopastoral systems. These techniques that prevent land degradation, promote conservation and restoration of soils and ecosystems, and reduce drought of water resources. So there are public policies and different activities that have a lot of trade-offs, and we can implement together. This solution, for example, in the case of the restoration of soils and preventing the land degradation, not only represent a mitigation action through carbon capture and storage, but also strengthens our production systems, consequently increasing the food security, and that, of course, benefit the people and the society. It is also crucial to highlight that climate change jeopardizes food security due to the water scarcity that all the world is facing. According to the Organization for Agriculture, drought could affect 8 million hectares of productive land, which represent 14% of the land for agriculture. So in this sense, agro-silvopastoral systems are also an ideal solution to increase the resiliency of the territories. Water in agriculture will continue to play a fundamental role in world food security. It is estimated that by 2050, the population of the planet will be approximately 10 billion inhabitants. And for this, it will be necessary to increase the food production by at least 50 to 70%. So the growth of food production will not be at the expense of the expansion of the agricultural land. That is very it is not recommendable. For the agriculture, we'll have to intensify and be more productive per hectare of crop, per animal unit, and particularly per cubic meter of water used. So likewise, we must incorporate indigenous people and local communities on these initiatives. As it promotes social justice, undoubtedly also the closely linked and directly dependent on natural ecosystems communities, they are, of course, interested on saving their livelihoods. So for the fulfillment of these actions, we need to guarantee international cooperation, capacity building, and knowledge transfer tools. It is also necessary to create and drive co-financing mechanisms to achieve the last goal, which is essential to bring a public and private funding together. The last goal is, of course, being more efficient in the water use. Climate change is a cross-cutting problem, and there are many elements to consider in order to face it. So this is the reason why I celebrate very much the organization of this event, which I am sure that will contribute with the necessary reflections to talk about the tools that are going to impulse transversal projects and provide international community options that will help to combat the climate change and this emergency in a common front. So I want to conclude by reiterating the importance of social component of the fight against climate change. This is something that we frequently missed or forget, as it is part of the historical fight against inequality, we have to remember that people who are living in situation of vulnerability are the most likely to experience the impacts or the effects of climate change, and also the impacts of the food insecurity, the water scarcity, the lack of financial support. So we still have the chance to change the reality of the communities that are vulnerable, and we can continue enhancing this work and all the previous efforts made before now. So thank you very much and wish you the best for this event.
Thank you, Madam Delgado. Thank you very much for your words and to be here with us, sharing in this event. Our third speaker now is Mr. Jonathan Day. He's Deputy Director of Risk Assessment and Investment of the Environment Agency. He is responsible for long-term investments and funding strategy for the Environment Agency's flood and coastal risk management function. This involves understanding risk in England by developing England's national flood risk assessment, evaluating potential future trends and investment needs, and developing the tools to invest at the right times in the right places. He has worked for the agency for the last 15 years, and we are really happy to share with him this conversation. So, Mr. Day, thank you to be here. So the mic is yours.
Thank you very much. Good afternoon, everyone. Buenos dias. I'm going to talk about climate change from an Environment Agency perspective, so I should explain who we are. The Environment Agency in England, in the water context, we're both an environmental regulator and an operator. So we regulate the privatised water industry in England to ensure we've got a clean and plentiful water supply. But in the flood context specifically, we're also an operator. So we build and we maintain river and sea flood defences. We operate flood warning services. We work with a whole range of partners to plan for and respond to flooding. Obviously, it goes without saying that climate change cuts across everything that we do. We sit on the delivery side rather than the policy side of this debate, so I'm probably not the best qualified person to present an overall context from a UK government perspective, but the key facts are probably pretty obvious. The UK is one of the first countries in the world to establish a formal net zero target. But arguably, we're yet to demonstrate that we've got the policies that will achieve that. And you could say the same again about the COP26 commitments. It's great to see so many countries come forward with commitments, but on a global level, we haven't yet stabilised emissions, let alone brought them down. So this is where my organisation enters the debate. Our view is that the climate emergency can only be successfully tackled through a greater focus on adapting to impacts that are inevitable. So impacts that we're already seeing and impacts that are going to become more severe, whatever happens. As a public body in the UK, we're obliged to report to government on our contribution to climate adaptation. And we actually did this in the run-up to the COP26 event. And we welcomed the fact that adaptation was one of the summit's 4 goals, but we did point out that there was in fact insufficient focus on adaptation and argued that more action is needed at a global level. So in our adaptation report, we talk about 5 reality checks, and I'm just going to relay those. Number 1, in Britain, the EA alone, the Environment Agency alone, can't protect everyone from increasing flood and coastal risks. So, for example, we're looking at extreme sea levels that used to occur on average around once a century could become almost annual events in some locations by 2100, will make some parts of our coastline unsustainable. Number 2, climate change makes it harder to ensure clean and plentiful water, most obviously placing stress on the public water supply, but also causing many and varied environmental issues. Number 3, regulation isn't yet ready in the UK for a changing climate. So, for example, we regulate water abstraction, and that legislation wasn't designed in the context of the sort of rapidly changing combinations of flow and demand that we're starting to see today, and we'll see more of in the future. Number 4, ecosystems can't adapt as fast as the climate is changing. The UK is in fact one of the worst countries historically for biodiversity loss. One example of that is historical loss of coastal wetlands, which, by the way, exacerbates flood risk and which we need to reverse. And finally, number 5, there will be more and worse environmental incidents. Over the last 15 years or so, we've seen multiple floods in Britain causing billions of pounds of damage. We do have quite sophisticated warning and response systems, but they're going to come increasingly under stress. So, for example, in England, we have 3 million properties at risk of surface water flooding, and we don't have an effective early warning system for that type of flooding as we do for river and sea flooding. So what do we want in the face of all of this? We want to see a nation working together to achieve climate resilience. We can't sit in the background preventing all of the impacts so that people don't notice. And focusing on floods specifically, which is my own area of work, as of 2020, we've got a new national flood and coastal erosion risk management strategy. And this puts creating a climate resilient nation at the heart of our approach. It shifts the dial from protection to resilience, and it's a call to action for all of our partners and for the public. We also have an ambitious net zero commitment of our own. So our flood operations are actually by far the biggest part of our carbon footprint. And by 2030, we want to lead by example by more than halving the direct emissions from our operations and
Sorry, I think we lost for a minute.
I'm sorry, my connection must have cut out. I'm not sure how much you you missed of that. Perhaps, would you like me just to conclude again?
Yeah, yes, please. I was lost for a minute too, so I'm saying you.
Apologies. I think I was just concluding on collaboration and understanding and just making the point that it's very important to us. We have a research program. We have an innovation program where we're testing approaches to our new strategy, and we openly publish everything associated with those programs. We have a lot to share with partners, but by the same token, we welcome opportunities to learn from innovation and experience in other countries, because we know that the scale and nature of the threat from climate change is changing all the time, and the impacts that we see in other countries today could very possibly be what we see in the UK tomorrow. So we're very, very happy to be part of these dialogues. Thank you very much, and apologies for my connection.
Thank you very much, Mr. Day. As we have to get used to the pandemic, also we have to get used to lost connection in our Zoom meetings. So it's perfectly normal. Thank you very much to be here. Now, I would like to introduce our next speaker, Mr. Germán Martínez Santoyo. He is the head of the Mexican National Water Commission, Agua. He is a civil engineer at the University of Mexico and a professional expert in hydraulics engineering by the Mexican College of Civil Engineering. He has formerly served as a Deputy General Director of Administration and as a head of the Northern Central River Basin Organization. Standing out, the administration of hydraulic and groundwater national resources, the programming and construction of hydraulic infrastructure, and for the agriculture development of La Comarca Lagunera. He also participated in cooperation projects between the Meteorological Service of the United States, El Salvador, Dominican Republic, Nicaragua, and Mexico for the development of hydrometeorological systems. We are honored to share this space with him. And Mr. Santoyo, now the mic is yours. Thank you very much.
Thank you very much, Jorge. Josefa Gonzalez Blanco, Ambassador of Mexico to the United Kingdom. Marta Delgado, Undersecretary for Multilateral Affairs and Human Rights. Jonathan Day, Deputy Director, Risk Assessment and Investment Environmental Agency. Good morning to all of you. I would like to thank the Mexican Institute of Water Technology and the Mexican Embassy for the United Kingdom for the kind invitation to participate in the inaugural event of this important encounter between experts from the United Kingdom and Mexico. The link between water and climate change is evident, and therefore achieving water security is now being understood as necessary, and it's becoming a global concern. Mexico is a country particularly vulnerable to the impacts of climate change due to its socioeconomic and geographic characteristics, which feature great contrast. The north part of the country, the most arid region, faces frequent drought in Mexico, while the south has heavy rainfall, which very often is the cause of severe flooding. This situation is aggravated since the biggest cities and productive centers, those with the highest GDP, are located where there is less water availability, while the region with the highest precipitation levels and more water are the poorest and more marginalized areas. Changes have been observed in the distribution of rainfall in the country, and according to the projections, there could be decrease up to 20% in the coming years, which will have an impact on the availability and quality of water and consequently on productive activities. The agriculture sector is one of the most endangered, and declines in the productivity of strategic crops and loss of soil fertility are expected, which could jeopardize food security. Furthermore, our country is constantly exposed to extreme weather phenomena, such as tropical cyclones on both coasts during more than half of the year, May to November. Climate change has intensified the hydrological cycle and has led to an increase in the phenomena and its consequent impacts on the population, infrastructure, and natural resources. The year 2020 was an example of such vulnerability, especially in the month of October, when moderate to extreme drought was recorded in more than the 35% of the country. On the other hand, heavy precipitations took place in the southeast region with an accumulated rainfall of more than 600 millimeters in a period of 7 days, causing flooding in 5 of the 32 states of the country. What are we doing in Mexico? The main objective of the National Water Resources Program of the government of the Mexican President Andrés Manuel López Obrador is to progressively guarantee the human rights to water and sanitation to all the population. But it also establishes that in order to face the impacts of climate variation, it is necessary to build capacities for adaptation to climate change, to protect the natural water resources, and above all, to consolidate the democratic governance of water in our country. For an adequate management of water resources as well as risk reduction, the federal government has established social participation as one of its public policy priorities, respecting the traditions of communities and indigenous groups within priority infrastructure projects. Example of this inclusive and collaborative policy can be found in different priority projects of the federal government that involves water components such as the Mayan Train, the interoceanic corridor of the Isthmus of Tehuantepec, the new Felipe Ángeles Airport, the healthy water for the Laguna region, and the Texcoco Ecological Park, among others. The latest Texcoco Ecological Park project considers the recovery of 12,200 hectares as an ecological restoration area for public use for the benefit of the inhabitants of the Valley of Mexico and the vulnerable population of the surrounding areas. Conagua develops large infrastructure projects for water supply, sanitation, and well-being of the population with an ecosystem approach that faces the challenges of water management and provides financial resources to the country's municipalities for the development of small water and sanitation projects. These funds are exclusively allocated for those actions that contribute to improving these services and that directly benefit the population, with a focus on priority attention zones, marginalized indigenous and Afro-Mexican population. Conagua also implements the National Drought Program through a system integrated with the North American Drought Monitor. We have developed a protocol to coordinate activities with different federal government agencies, such as the Ministries of National Defense and the Navy, as well as the National Coordination of Civil Protection, to address climate emergencies, but before and after the events, supporting the necessary reconstruction works. Finally, as a complement to the Sowing Life program, Programa Sembrando Vida of the government of Mexico, which focuses our restoration and the well-being of the population in rural areas. Support is given to the farmers' learning communities for the acquisition of systems for water collection, extraction, storage, or irrigation in their communities. This program also represents benefits in terms of mitigation and is projected to be exported to various countries from Central America. Sustainable water management must be an integrated undertaking. To be successful, it needs the participation of all water users, society, productive sectors, and public authorities of all levels. Recognizing the evident link between water and climate change, aware of the vulnerability of our country, and considering that the challenges we are currently facing are interconnected and cannot be met with a sectoral silo approach, the government of Mexico considers water as a pillar of well-being and is changing the paradigm of water management, proposing collaborative and inclusive solutions for the benefit of all, with special attention to the most marginalized population. Thank you very much, and I wish the next 2 days are very successful. Thank you.
Thank you very much, Mr. Santoyo. Now we're going to our last speaker of this opening session, is Dr. Adrian Pedroso Acuña. He is currently the head of the Mexican Institute of Water Technology, a civil engineer from the National Autonomous University of Mexico, and a doctorate in engineering from the University of Plymouth in the United Kingdom. He is a licensed senior researcher from the Institute of Engineering of UNAM. He's currently a Level 3 national researcher and a World Bank consultant. His scientific work has more than 100 publications, and he served as the department head of hydraulics at the Engineering Institute of UNAM. He is also the creator of the Real-Time Hydrological Observatory, a task that allowed monitoring the hydrological cycle in real time in Mexico City area. He is an expert on water policy and an enthusiast of water ethics. Dr. Pedroso, thank you to be here.
Many thanks, Jorge. Her Excellency, Madam Ambassador of Mexico to the UK, Josefa Gonzalez Blanco, very good morning. Dear Undersecretary for Multilateral Affairs, Marta Delgado, thank you for being here. Dear Deputy Director of Risk Assessment and Investment of the Environment Agency, Jonathan Day, thank you for your presence here today with us. Dear Director of the Mexican Water Commission, Germán Martínez, thank you also to you to be here with us this morning. Good afternoon to you all in the UK and good morning here in Mexico. It's a great pleasure for me to speak before to you today in this inauguration. Before I start, I would like to say a few words on the reasons that motivated us to start this important dialogue between our countries. As far as back as the 1980s, climate models indicated that changes in patterns and amounts of precipitation would be an important consequence of climate change. Growing demands for water, even without the added burden of climate change, are placing enormous stress on water resources all over the world. Today, the evidence that we are altering the climate is undeniable. Furthermore, the impacts of global climate change on water are enormous. Water is the key driver of impacts. We now see how rapid loss of glaciers has an influence in the timing and volume of river flows. Also, higher temperatures increase water demand and intensify heat waves and forest fires. Therefore, it is now recognized that the climate crisis is indeed a water crisis. As humanity, we have forced an evolution of the Earth from a variable but stable climate to a constantly evolving, changing, and worsening set of conditions. Not all climate impacts are created equal or distributed equally. Resulting adverse impacts are not felt equitable among people or nations. From extreme weather to rising sea levels, the effects of climate change often have disproportionate effects on marginalized or underserved communities. This is why it is time for a fundamental change in the way we think about water. In the 20th century, the focus of water management was on enhancing supply by building massive dams to capture water in wet periods to use in dry ones, and long pipelines to move water from areas of abundance to areas of scarcity. That approach brought benefits to some parts of the world, but also led to unanticipated costs, both social and environmental. Today, the COVID-19 pandemic has made evident not only that the human health is linked to that of the environment, but also to the global economy. Indeed, in some countries, it is through their economic, political, and cultural ties with other nations that the impacts of climate change are most likely to be felt. Indirect impacts through, for example, the international trade or the migration of people are also very important. If the water crisis is the key driver of the climate crisis, we need scientific solutions, companies and universities from all over the world to work together to tackle them. Conferences such as the one we have today allow us to do that, bringing together a group of specialists with expertise across water, agriculture, and economics. Therefore, this dialogue enables the collaborative identification of the right connections to make rapid progress. The goal of this binational conference is to harness the power of science, engineering, and knowledge to build a sustainable society and an inclusive economy that works for everyone. Collaboration and innovation are necessary ingredients for the future, yes. We are better together. That is the way to transform the equation from one of water scarcity to one that provides hope for everyone. In Mexico, we are convinced that water can be the driver of an equitable economic development, but for this, we need to evolve and prioritize the protection of the most vulnerable. If the process of this urgent transformation is not just, the outcome will never be. The evolution itself must be just and equitable. That means using less to produce more, treating and reusing more wastewater, meeting the human right to water for all, and developing nature-based solutions. Our decision-making process must be adjusted to reflect a diverse set of realities and climate all over the world and also within countries. Therefore, during these 2 days, I wish you all fruitful discussions to overcome the era of overexploitation of aquifers and catchments. We need the best science to find the best solutions. Let us catalyze the transformation of water institutions, technologies, and policies of our two countries to build together a resilient home for our daughters and sons. The whole world is connected. We therefore need to think collectively, but always with a lens of justice, solidarity, and respect. We believe this is an ethical imperative for us all. As the great Mexican president Benito Juárez used to say, among individuals as among nations, respect for the rights of others is peace. We could add to this quote that those rights include economic development and well-being for all. That's why in the Institute we have the three principles of ethics, transparency, and science-based decision-making. I wish you all good discussions and a magnificent conference during these 2 days. Many thanks.
Thank you very much, Dr. Pedroso, and thank you very much all to our high-level opening panel. After hearing you all, we are really excited to start with the program. We invite you to stay tuned to these 2 days of scientific events. We are really pleased to start, and we are excited. So without further ado, let me introduce to our next presenter, moderator, Agustin Breña. He's gonna, we're gonna be with us in the next event, the first roundtable that we're gonna start. Thank you very much all again. We cannot be as happy as we are right now. So Agustin, please, the mic is yours. Thank you very much to let me be here with you today.
Thank you, Jorge. Hello, everyone. Good afternoon in the UK. Good morning in Mexico. My name is Agustin Breña. I am Deputy Director at IMTA, and I will be chairing this first roundtable, where we have 5 experts, 3 from UK and 2 from Mexico, and their talks will address different issues related to climate change and water resources. In this panel, each speaker will have up to 10 minutes to present, followed by the next one, and at the end of the 5 speakers, we'll have about another 10 minutes for questions. In case we run out of time, I will provide the questions to each speaker. So our first speaker is Professor Albert Chen from the University of Exeter, who will speak about climate change and public health from a water perspective. I will read very quickly his bio. So Professor Chen is an associate professor at the Center for Water Systems at the University of Exeter, with over 20 years of experience in water and human environmental studies. He has been working on flood risk assessment and developed a series of modeling tools to advance scientific knowledge on the interrelationships between different phenomena, services, and consequences related to water, human, and environment. His main research topics include water resources, hydrology, hydraulics, hydroinformatics, water and health, hazard impact assessment, disaster risk management, climate change adaptations, and resilience strategies. So please, Professor Chen, the microphone is yours. You have 10 minutes. Thank you.
Thank you. Thank you, Augustine. Good morning, everyone, and good afternoon, everyone. My name is Albert Chen. I'm an associate professor of the water and human environment at the University of Exeter. It's my pleasure to be here today to share what we've been doing in climate change impact and the water resource disaster and the human health research area with you. So today I'm going to give you a quick introduction. So here is that we've been listening to what the ambassador and Madam Secretary they already highlight the importance about the climate change. That's how this will affect our society. So in this, when there's a climate change, now that we have seen some change of the water resource distribution because the temperature changing affecting, driving the change of precipitation around the world and leading to the different uneven, more extreme uneven distribution of water resource around the world. And this also led to some huge problem for the environment, leading to the challenge of the water quality management. And on the other hand, we also seen this witness that sea level rise in many, many coastal countries and affecting the community, and that increased the flooding of the coastal flooding, but also combining with the extreme weather event driven by temperature change, the rainfall change, also affect the likelihood of the flooding in many parts of the world. And again, this changing temperature also affect this likelihood of heat wave and leading to the droughts in many parts of the world. And all of these, they have the impact that not only to the property, but more importantly, they're having huge impact on those human health. So that's why we have been interested in Exeter University. We've been looking into these areas. So because of climate change, we see that already some area around the world, they already have very not so good water security in many parts of the area. So that's due to the changing trend of the precipitation, they might lead to the even worse conditions. So on the top right, you can see this for the projection for the future. There are quite a lot of proportion of countries they will have very extreme water stress. They have very little water available per person for every year. So that certainly will lead to the health problem when people don't have the clean water to drink, of the water sanitation. So that will increase the likelihood to get having the higher chance of getting illness, particularly related to waterborne and vector-borne disease, as you can see on the bottom left. So here is an indicator of this different for the vectors around the world, the distribution. And because the change of temperature, this vector, their habitat might expand to wider area, and also will lead to more community being facing the risk of this vector-borne disease. On the right-hand side, you can see this. The map is a country map in proportion of the coral case. The coral is also related to water. When you can compare to the figure on the top and on the top left, you can see there's those countries that are more highly associated to those countries with the poor water availability or water security. So, and because the climate change is more likely to have more extreme conditions for those countries. So that's why we have been interested in looking into this area. As the Madam Ambassador and also Madam Under Secretary also highlight this, because the climate change increased the extreme rainfall events, extreme hazard events. So on the top left, now we are seeing more often some scenario like you have continuous cyclones or hurricanes happening in very consecutive period of time and leading to more devastating damage to different areas. And on the bottom left, you can see the increase of extreme hurricanes event compared to the 1975 to 1990 period of time, and the 1990 to 2005, you have seen a significant change in many all parts of the world. There are more extreme hurricane events happening, and that will lead to more widespread flooding. That's you can see on the top right. So there a huge area could be inundated due to this extreme event, and that also lead to this disruption not only for the damage for the property, but also disruption of all this supply chain. And again, this may also affect the production of the food, and that's causing problem for the human health. And on the bottom right, you will see this on the opposite side. So instead of having too much water, we have too high temperature that could lead to this extreme heat wave and causing a forest fire, wildfire. And because in that case, we normally have less water resources for those part of world, and that will increase the difficulty to manage this kind of scenarios. So as a result, we try to focus on this, how this flood will impact on the human health. And in different projects we have conducted recently. And so the first one I want to introduce you is this one. We try to look into the flooding, how this flooding associates to the pollutant and the pathogen propagation. So on the right-hand side, you see a map. It's not flood map. It's the concentration of pathogen. So a lot with the flood water. So we build this model to simulate the dynamic of water in the sewer network, also on the surface. And that with this information combined with the water quality data in order to analyze how the water quality will change in the community. And that some of this pollutant that might lead to a very significant health impact, as you can see on the bottom left, or there could be some infectious disease of passengers spreading in the community, causing the challenges of the public health. So as a result, we adopt this approach called the Quantitative Microbial Risk Assessment, QMRA. That's the way we try to quantify this risk associated to the flooding and on the public health. So first of all, we try to use, as I said, we use the hydraulic model to simulate the dynamic of a flood, and combining with the water quality, we'll be able to find out what's the dilution and what's the concentration of the different pathogens in this flood water. Then we combine with other information such as the exposure of the different people, different population, and in those areas, and then combining with some for different age population group and also gender group, we identify the possibility of them, those different vulnerability for people who have contact with the polluted water. So what's the likelihood they will get illness? As a result, we use a Monte Carlo simulation to run a lot of scenarios to see what's the possible combination of different conditions. And that with those information, we will be able to create a map or statistical information of the probability of infection for different type of demographic group where they were exposed to the disease, the risk of the pollutant of pathogens, and leading to the so we can quantify how's the likelihood, how many people would be affected by this pollution in the water and affecting their health. And the other one research we've been working recently is working with partners and try to look into the combination of the hazard and the public health. And so how can we better manage both areas? So the idea is try to analyze the flood hazard and combining with the water effect on the public health, particularly looking at the waterborne disease like cholera, and that's in the communities, and to see how can we further develop different technology or different interventions in order to help us to better prepare the community against the coming threat of a climate hazard, and also improve their protection and the resilience to this public health waterborne disease, and to help them to reduce the impact of this climate change. So that's where we did in this approach. We try to look into build a framework in order to analyze this risk for a lot different scales. So if we look into the national scale, we look into long-term planning. So we are trying to see how can climate change for future decades. So how would this affect the community in different parts of countries? And gradually we go to the more detailed area to look into the regional area, try to look into how can we enhance the preparation of the society by looking into different investment or in the infrastructure or investment of the public health care to prepare the community in order to cope with the challenges. And for the shorter term, we try to look into the crisis management. So for the emergency, if there's some coming flood or weather hazards, so which area could be are more likely to be hit first? That's where we are going to allocate more resources or more labors to help those people, those vulnerable communities to cope with the coming threat. And after the event, we also want to look into how can we help the people the community to build back better and to enhance their capacity for the next coming event. So this would adopt this kind of hybrid approach by looking into a different scale of the lead time for different planning to develop the plans for coping with the climate change and for the very long term, and then for the slightly shorter term, we look into the season forecast to prepare the community, society against the coming disaster and the public health and the coming seasons. And for the very short term, we try to look in the events, the weather events, how can we better prepare the society to mitigate the damage and the impact of the coming extreme weather, or maybe flooding or drought, and to improve our protection to the communities. So the next one is not really about climate change, but it's what we are all experiencing at this moment. That's the work we recently developed, and try to look into how can we use the water, our intelligence in water, to better predict the spread of COVID in the communities, and to better inform the public health manager to adapt to make a quick decision to prevent the spread of the COVID-19 in our community. So this one, we try to look into the water try to take the measurement from the wastewater, combining with the biomarker information within the wastewater, so we be able to analyze how's the population and which area in the communities they are more likely have higher potential COVID-19 case, because that's the measurement we take from the wastewater. People might already been infected by the virus, but they don't have any symptom yet. So by using this technology, we will be able to identify which area they are more have higher potential in order to to enhance our public health facility or service for those areas, or try to implement some response measures, try to reduce the spread of COVID-19 in the communities and to better protect the public health. So that's recently what we've been done in the project related to the COVID-19. So
1 minute left, please.
So I just kind of thank you. I would like to thank you everyone for your listening, and we've been doing quite a lot of different activities. They've been supported by different funding bodies, and we are also looking forward to this, having the opportunity to work with partners in Mexico, try to further advance the science and to better improve our capacity for predicting the weather hazards and climate hazard, and to better prepare the community against the future climate impact and to protect public health. So here is my contact. And so thank you very much. And so I hope if you have any question, feel free to contact me. Thank you.
Great lecture, Professor Chen. We thank you very much. Now we continue with our second panelist, who's Professor Akbar Javadi, who's also at the University of Exeter. Professor Javadi, he's a professor of civil geotechnical engineering. He's also the head of the computational geomechanics group and director of global development in the Department of Engineering at the University of Exeter. He has over 24 years of research, teaching, and consulting experience in various disciplines of engineering. He's also an honorary visiting professor at the University of Shanghai for Science and Technology in China. He's a chartered engineer and fellow of Institution of Civil Engineers. His main research interests include development and applications of numerical modeling techniques and computer models for a wide range of engineering systems, as well as optimization and artificial intelligence. Thank you very much, Professor Javadi, and the floor is yours.
Thank you very much, Agustin, for the introduction, and good morning and good afternoon to colleagues in Mexico and United Kingdom. It's a great pleasure to be here with colleagues, and I would like to talk about the research that I've been doing in the last 12 to 15 years on developing numerical models and control systems for seawater intrusion, considering the effect of climate change and sea level rise. I would like to acknowledge contribution to this research by my PhD students and academic colleagues. I will talk a little bit about the model that we have developed for simulation of seawater intrusion, new methodologies that we have proposed for controlling seawater intrusion, and some optimization models we have used to optimize the arrangements for the proposed seawater intrusion control method. And then I'll talk a bit about work on simulating the effect of sea level rise and also over abstraction and combination of the two, and show the applications to some case studies. Just as a background, about 70% of world population live in coastal areas, and many of these coastal regions for their water supply depend either entirely or mainly to groundwater resources. In coastal areas, groundwater is in direct contact with saline water under the sea. And with increasing population, there's increase in water demand. As a result, there's an increased abstraction from water, which results in intrusion of saline water into aquifers. On the other hand, with sea level rise, the head of saline water increases, which again pushes the salinity further into groundwater. The problem is very small percent of salinity in groundwater could make it unsuitable for human use or any other uses. There are many countries that have lost their coastal aquifers to seawater intrusion, so there's an urgent need to control seawater intrusion. Looking at the projected levels of groundwater abstraction throughout the world, we can see an increasing trend. Everywhere we are increasing abstraction from groundwater, which leads to seawater intrusion in coastal aquifers. For this research, we have started with developing a numerical simulation model to simulate flow of water, salinity in soils, adapted it to simulating seawater intrusion. And we have validated against standard benchmark problems and against analytical and other numerical simulations. Then we have used the model to propose a new method for controlling seawater intrusion, which is based on abstracting the saline water and at the same time recharging the aquifer with treated wastewater, with stormwater, other sources of water. And this abstracted water can either be dumped in the sea, or in areas of the world where there is a water scarcity, it can be desalinated and used as part of water supply. We have also had proposed a similar method to the previous method, but this time the recharge can be done by gravity using surface ponds or tanks under the ground. We have developed a simulation optimization model in order to optimize the arrangement that we proposed in the previous method of control. And we have applied it to a number of case studies, including benchmark problem. Basically, we have formulated the problem as an optimization problem. So if we are going to use abstraction and recharge, what would be the optimal location for abstraction and recharge wells in terms of distance from shoreline? What would be the optimal depth for each well? At what rate we need to abstract? At what rate we need to recharge in order to minimize the overall cost and minimize the salinity in the aquifer? Of course, subject to some practical constraints. So this is just a summary result of this application to a benchmark problem. And we have shown that compared to existing methods of like abstraction only or recharge only, our proposed method can significantly reduce the cost, significantly reduce the salinity in the aquifer, and can push back the interface between saline water and fresh water further towards the sea and create larger volume for fresh water. We have done the same for the other method, but by gravity recharge. We've done similar optimization without going too much detail. We have shown that our proposed method can reduce the salinity by 65% compared to 26% for abstraction only at much reduced cost, at quarter of the cost of abstraction. We have also used some multi-objective approaches in order to trade off between different objectives of cost and salinity in the aquifer. For the second case, we compared it with recharge only and abstraction only, our method. And we have shown that the trade-off that our proposed model will produce significantly reduces the cost and reduces the salinity compared to other methods. So the advantage of this approach is decision makers will have a lot of options to choose from depending on what trade-off they can accept in terms of salinity and cost. The next study that we have done is the effect of sea level rise on salinity intrusion. Well, by increasing the sea level rise, obviously head of saline water increases, which pushes the salinity further towards the land. On the other hand, depending on the slope of the shoreline, a large area of the ground can be inundated, flooded by rising sea levels, which further moves the interface between saline water and fresh water, so exacerbate the situation. Here we have looked at different scenarios, the effect of sea level rise without considering this land flooding, the effect of this flooding as well as sea level rise, and also combined the effect of sea level rise and over abstraction in the form of lowering of groundwater table. So we applied it to, again, a benchmark problem. This is the current situation. We did this in 2014, distribution of salinity in the ground at that time. And for sea level rise, we considered a moderate increase in sea levels based on IPCC recommendation that by end of the century, we assume gradually the sea level rise will rise by 0.65 meters. Here we show the interface between saline water and fresh water. And we've shown that by increasing sea levels, the interface will move gradually towards the land, towards the groundwater. And this shows how it gradually moves in different years throughout the century. In that analysis, we did not include the effect of land flooded by seawater intrusion. Here we considered the effect of slope of the ground as well. And we have analyzed it for different slopes. We have shown that the flatter the slope is, obviously, a larger area of land is flooded, and the intrusion can be significantly more than the assumption of no flooding. And this is the results for the start of the analysis, 2014, and this is for end of the century, where the gradual movement of salinity is predicted. For the last scenario, we analyzed the combined effect of sea level rise and lowering of the groundwater level for over-abstraction. And we see that in this case, combined effect of over-abstraction and sea level rise could almost entirely contaminate the groundwater in this case. So this is a comparison between the combined effect of sea level rise and lower groundwater only sea level rise. We have applied this modeling and optimization and control method to a number of real case studies in United Arab Emirates, Wadi Ham Aquifer, in Nile Delta in Egypt, Gaza Strip in Palestine, Pingtung in Taiwan. In Taiwan, we also looked into integrated management of surface water and groundwater resources. In this case, we tried to see how we can use flooding against the seawater intrusion using the proposed methods. So I would like to end here, and I would like to acknowledge the funding that we have received for this from British Council and Royal Society. And again, I would be very interested to discuss if this topic is of interest. Here's my contact details. Thank you very much for your attention.
Thank you, Professor Javadi, for this excellent presentation. Our next speaker is Dr. Hind Saidani Scott from Bristol University. Her presentation focuses on the water energy nexus. Dr. Hind Saidani Scott is a senior lecturer in mechanical engineering at Bristol University. After graduating with a degree in physics from Algiers University of Science and Technology, she followed with a master's degree and a doctorate at École Nationale Supérieure de Mécanique d'Aérotechnique. And then she undertook another PhD at Bristol about heat and mass transfer in porous media with application to building materials. Afterwards, she spent some time in Japan with a scholarship from the Royal Society. And after that, she came back to UK, where she was appointed. She was the first female lecturer in mechanical engineering at Bristol University. And beyond her research activities and teaching activities, she's been very active in the promotion of science subjects to the school children, and also as a member of the Women Engineering Society, and where she's mentoring young women in engineering. So thank you very much, Dr. Hind Saidani, for your time, and you're welcome to present your talk.
I don't know if you see it. Can you see my talk?
Yes, we can see it.
Can you see it now in the projection style?
Yes, it's fine.
Okay, thanks. Okay, my name is Hind Saidani Scott, and I'm senior lecturer in Bristol University in the mechanical engineer. My talk today is about novel methods for cooling PV, solar panel, and desalination or purification. First, just a small introduction to Bristol University and the Cabot Institute. I am part of course, Bristol University of the Mechanical Engineering Department, but also of the Cabot Institute. I just put here some web page and statistics. The first one is for the University of Bristol. The biggest research group about water is in civil engineering. Is in civil engineering. Of course, there are other groups in hydrology and geology, which will be presented by Jeffrey later. I just put here 4 statistics, which I find a bit funny. One, which is Bristol is the top 10 university in the world. We are 32 highly rated in 10 in the UK top universities, 32 in the world, 7 of the most targeted by UK recruiters. But the best one is we are the 11th world cooled least destination. I don't know how they define it, but I find it cool. Solar energy development in recent years, solar deployment has skyrocketed for a number of reasons. Increased energy requirement, greater availability of incentive, lower cost, improved technology, more investment, ambitious climate target. And as a result of that, solar farms have grown larger and more widespread. And I put just some example here with Egypt. And if we go from the right bottom left, so we have Egypt, we have the one in Morocco, we have the one in the USA, we have the one in India, we have in China, and you have one in Mexico. Of course, there are a lot more than one in China. There was a lot more than one in India. Same for the USA. So especially these last 5 years, they just really skyrocketed all over the world. What is the fact about solar energy? There are a few shortcomings to this, which face this industry. First is the relatively low energy conversion and high efficiency degradation with temperature rise. A lot of people don't know that. First, when we have the solar, we don't just have to put the solar energy and everything convert up to 80% or 70%. That's a dream. That's not happening. The average conversion factor is around 22 to 30% for the very good ones. So we are not really catching all the solar energy, solar radiation. On the top of that problem, not just the ambient temperature, not just the environmental temperature when it rises, but also the material, the solar panels, when they are very hot due to increase of temperature because they are exposed to the sun by radiation or everything, their efficiency is going to drop. If you think that perhaps more than 70% of the solar plants, the big ones, have been built in desert, that tell you the kind of temperature we have between 10 o'clock and 4 o'clock in the afternoon. So here there is a fact. First, it's only 19% of incident solar radiation which is converted into electricity. It has improved a bit. Now it's between 22 and 30 for the best ones. The other fact is each temperature degree increase more than the standard temperature, which is more than, let's say, between 22 and 25. The efficiency reduced by 0.4, 0.5%. Technical solutions. We have various solutions to solve this problem. One is the active system. So we just put a fan and a pump, or we pump cold water, or we blow cold air. It's a power consumable. So all the energy you are going to gain already what you are losing at very high temperature, you are going to use it to run these fans. So it's not very economical. It's based on forced convection, which is better than natural convection. But it is an effective cooling system because it's forced and it's directly in contact. The other methods are what we call passive systems. So we don't use any power consumption. They are based on natural convection, so we can leave the air just by itself circulating if it is cooler, which is not always the case. It's less efficient than forced convection. It is good, acceptable cooling performance. And the material that we are using for cooling, we attach it on under the PV panels. That's going to, both methods eliminate some heat. They're taking the heat from the solar panel, and then we can use this heat. We can either use it for recovery from the PVT, what we call PV, it's photovoltaic but thermal panel, where we heat the water, and we use it either for heating, for air conditioning, or for other things. And the other one, we can just dump it in the air. So in our group, our research objective first is to search for sustainable solution for enhancing thermal and electrical performance of PV panels and benefit from the absorbed heat, which is in the material. For other applications, it can be heating, humidifying, water generation for greenhouses, or even cooling. The second is applying new innovative systems that use different heat and mass transfer mechanisms for cooling solar panels. I'm going to speak a bit more about that. Using nanotechnology for increasing thermoconductivity and the system efficiency. And from that, developing a new nano-hybrid PV system with eco-exergis study, which show that it is feasible, durable, sustainable, and based on renewable sources. So what we are doing, and I'm going to go quickly and explain. So we have an experimental. The majority of my work is experimental, and we do analytical, but we have done some simulation. But the majority is experimental. So we have a laboratory, which is the thermofluid lab at Bristol in the engineering faculty. And so we have a heat source which is simulating the solar energy, and we put the different material. We always have a reference material, and then we can change the irradiance from 1,000 or 800. What we are doing, we want to cool our solar panels by materials that we are putting under the solar panel. So what we do, for example, we wet them in the night, let them being saturated like zeolite, and we have zeolite here, which is also activated alumina here. We have hydrogel beads, which is figure 4, and we saturate them with water. I don't know if a lot of you know what is zeolite. Zeolite, they are solid tablets, so their volume doesn't really change, but they are very porous and they absorb the water. The second one is hydrogel. I think a lot of you have already seen that. They are really very solid, very small bits, and then when you put them in water, they take up to 500% of their volume of water. And we put them around plants, or we put them around other places where we want to keep humidity, but not water content, but just humidity. And they keep evaporating. The water is evaporating from the hydrogel and keep the environment humid. So we are using this. We have used these two elements, the zeolite and the hydrogel, to cool the PV panel. So what we do, we put them in water all night, and in the morning we put them under the solar panels. And what we do is we study the thickness which is needed to cover the complete range of temperature from 10 o'clock until 4 o'clock, with the maximum, of course, let's imagine between 12 and 2. So to cover all that. So the water, when it evaporates, we have the latent heat of evaporation. It's cooling the back of the solar panel and making it a lot more efficient. That is one experiment. So we did it with pure water. Then we did it with salinated water. We did a lot of experiments with different salination, from the most salted, simulating the most salted sea in the world to the less salted one, and changing the thickness of the hydrogels and the zeolites. We also
have 1 minute left.
Yes. Also, we have saturated them with nanoparticles, which is aluminium AlO3 and CO. Here is the result. The only thing is, very quickly, we can see here that the one which brings a very nice temperature reduction, which is nearly 18 degrees, is the hydrogel with nanoparticle of aluminium oxide. And this is with copper. So they are the top ones. I just made a comment in the bottom there. In these results, environmental impact due to the material used hasn't been taken into consideration. The result could be different if all aspects, environment, sociological, sustainability, ethical, are considered, not just financial. My collaboration wish is my collaboration could be with chemists and chemical engineer for the characterization of zeolite and hydrogel, to develop new hydrogel materials with nano additive, to study and develop phase change material for energy storage also, and develop of experimental, analytical, and numerical studies. All that to recuperate the water which evaporates and desalinate it if it is salinated. So that's the kind of study that we are doing, and we want to do more of it. Thank you. Thank you very much.
Thank you. A very insightful presentation, Dr. Saidani Scott.
Thank you.
Now we'll move to Mexico with our two last participants. We'll start with Dr. Iskra Mejia from IMTA. She's an undergraduate course on civil engineering, and then she studied a master's degree in hydraulics at the Faculty of Engineering at UNAM. Following that, she was awarded a scholarship from CONACYT to undertake her doctoral studies at the University of Bristol, where she completed a PhD in urban hydrometeorology. She's currently head of the hydrometeorology department at IMTA, where she oversees and participates in projects regarding extreme events. She's also a member of the National Working Group of the Intersecretariat Commission on Climate Change, which observes the timely and adequate compliance of the submitted nationally determined contributions. So please, Dr. Mejia, the microphone is yours.
Thank you very much, Dr. Agustin. So I'm going to show you some of the water challenges and the climate change scenario in Mexico. Would you mind confirming if you can see the presentation, please?
Yes, we can see.
Brilliant, thank you. Thank you for the opportunity. I'm definitely going to try to make the most of this chance of being the first Mexican presenter. I'm going to jump straight into the impact of climate change, given that we've already heard about the context of it by our outstanding speakers at the beginning of this conference. So starting by the factors that shape the water challenges in Mexico, we've already heard that Mexico has a wide variety of climates, and all these factors have an influence on the intensity and the spatial and temporal distribution of precipitation. We have an average annual precipitation of around 770 millimeters, and we also have conditions of both flood and droughts. And these two conditions are present in many parts of the country, and we've found it throughout its history. We also have tropical cyclones that transport significant amounts of humidity from the oceans to the continental zone. And all those processes contribute to the natural replenishment of both surface and groundwater resources. There's also, again, we have a marked condition of vulnerability of urban areas, of population areas. In Mexico, around 162,000 square kilometers are exposed to any type of flood risk. Also, around 3/4 of the population is where 1/3 of the renewable water resources are. So all this combined with their water pollution have a severe limitation to water availability, as have been accounted around 70% of the aquifers have some sort of pollution, according to the Quality Monitoring Network of Surface Water in Mexico. There's around 5,000 sites or stations that we can compare this information with. Regarding surface water, we have 757 basins, out of which around 650 have water availability, as shown in the upper right figure. Regarding groundwater availability, there are 653 aquifers, out of which a little over 400 have only water availability. Therefore, water security does become a demanding issue, given that we have these both extremes that I already mentioned. On one hand, we have arid and semi-arid regions that are prone to droughts. And on the other hand, we also have regions where the extreme hydrometeorological events favor floods. So what are the main challenges of water security? First of all, I'd like to define what water security is. So in this context, water security are the practices that ensure sustainable water supply for everyone under equitable conditions to promote health, economical growth, the conservation of the environment, and it also protects, given an acceptable level of risk, the population, and also other productive systems from the negative impacts of hydrometeorological extreme events. And it also involves mitigation and adaptation measures for climate change under the scenario that I already mentioned. Now, the main challenges for this to reach actual water security are seen through water shortages and also the pollution of water bodies. we have, again, the negative impacts of these extreme events. We also have to consider the conflicts around water and the environmental deterioration of basins and aquifers. And the main factors that induce or that exacerbate all these risks for water security are the demographic processes, the growing food demands, and this is also due to demographic growth, changes in the diet of the population, changes in the water demand for energy production, the effects of climate change, and inefficient water management practices. So this diagram that I'm showing is pretty much a summary of what I've just mentioned regarding the main challenges of water security. So we have the challenges, and then on the right side, we also have the risk triggers. They're grouping sectors because this way it allows us to determine more specific solutions and outline better objectives for the projects. So it's really important to determine which sector or which are the triggers for these challenges of the water security. So that, because something I repeated along any talk that I've given, you can't improve or you can't measure. So it's important to identify the sectors to have a better outline of what is the problem that we're facing. And to add to all of this, we also have the impacts of climate change. So in this case, the main impacts are going to be seen precisely in the hydrological cycle, as we've already heard. And in the case of Mexico, the recent studies estimate that by the end of the century, we'll have a decrease of precipitation of around 15%. There's also a decrease in surface runoff and aquifer recharge that ultimately determines the availability. This will be enhanced by climate change, because part of the precipitation is going to be retained and evaporated in soil and vegetation without even reaching surface water bodies or any of the groundwater storages. There's also a great area of opportunity to do detailed studies. For example, there is studies that IMTA has made in the basins of the north and the transboundary basins regarding what's the water availability using satellite-derived information. In the case of food production in areas with irrigation problems, we will also have to add the problematic of a wider or larger climatic variability. So here I'm talking about more frequent and intense droughts, followed by intense precipitation periods. And in general, this will lead to a lower water availability. So I'm going to present quickly a couple of projects that are being developed at IMTA. The first one is about real-time forecasting of intense precipitation in urban areas. And the second one is a project aimed at desalting groundwater through solar energy for irrigation purposes. Regarding the first project, this is pretty much a combination of all the available tools to provide real-time forecasting of intense precipitation in urban areas, where we are developing these informatic systems for the analysis, short-range numerical forecasting and visualization of intense precipitation in 3 urban areas. So we are combining the most updated tools to provide these real-time forecasts and to reduce field risks. So we're using weather radars, satellite-derived information, statistical methods, numerical weather prediction model, so that we can provide this pretty much this nowcasting for the urban areas, where, as we know, most of the precipitation, or the huge part of the precipitation that falls into these urban areas, is transformed directly into surface runoff that can lead to flooding. One of the biggest advantages of this project is that we're using only open access tools, as in if there is any possibility of expanding the tool to more areas or to other case studies, that can also be done if we disregard the computational power. We're using only open access tools. This system is being developed for the National Weather System in Mexico, and we're going to provide information through a visualization platform that's going to contain the outputs of the numerical weather prediction modeling for the 3 areas, as we can see on the left. We also provide information on the number of days with favorable conditions for convective storms using information from ERA 5. And we're also providing an analysis to determine the probability of severe storms. All these systems are going to be provided for the urban areas. And as I mentioned, the radar information will be provided for the metropolitan area of Mexico City. Then we also have another project that's about salting of groundwater through solar energy for irrigation purposes. And here the objective is, as shown in the slide, to implement a water desalting system for small-scale irrigation purposes. So in this case, we have a technification in 4 stages that are shown in the slide, where the main actions will include installing of a desalting system in a 600 square meter field. So this is just a test field in the north of the country. Regarding the practices that you see in the slide, we also provide training in soil management and irrigation practices. And this is something that characterizes the tasks of IMTA, as in we do develop technology as much as we also make sure that this technology is adequately transferred to the ones that are going to be applying it at long term. Other actions that are included in this project are the biological control of plagues, solar pumping, groundwater desalting systems to provide water for animals, and also water for forest irrigation. Regarding the solar platform that we're using and also the tree nursery that's being implemented in this project, regarding the solar platform, some of the actions implemented are the installing of these solar pumps that I've already mentioned, the installation of solar desalting systems for water consumption for both animals and humans. One of the key components of the project, again, is desalting water for reforestation techniques, which means that we might be able to use this resource for an area that definitely requires it. There's also drying chambers that provide organic bricks as a substitute of firewood. And regarding the tree nursery or vivero, that's also implemented. In this project. That just happened. We are including diagnosis and study of the viability of the project, of course, because we also want to make sure that this can be upscaled. There's the implementation of these beds where we can test all the methods that are included in the project. And again, regarding the use of all the tools that are included, we do provide training, and also we make sure that the people that are going to be implementing these methods and systems have proper training and that are adequately trained to again make sure that the project is going to be applied long term and not only during the duration of the action of IMTA.
You have 1 minute left.
Thank you very much. Just perfect to give the main messages. So the points that I would like for you to take home are mainly 3. So regarding water governance, this requires solving the complex problematic scenario that's been already described. An essential component, this is point number 2, to adequately address the challenges of water security is knowledge and innovation generation. We definitely need a better understanding of both the natural and social processes that are involved in water management, highlighting the importance of considering all the anthropogenic factors. This has to be, of course, under the adequate legal frameworks to make sure that water governance is appropriately observed. And finally, water security in many countries has become a matter of national security. And no country can minimize the urgency of achieving adequate water governance through research and, of course, international collaboration. That would be everything from my parts. So thank you very much for your attention.
Thank you, Dr. Mejia, for your talk. And last but not least, Dr. Antonio Salinas, also from IMTA, will talk about climate change scenarios. Dr. Jose Antonio Salinas, he's a researcher at IMTA. He has a background in physical oceanography from University of Baja California, followed by a master's degree in computer science at Monterrey Tech, and then a PhD in atmospheric physics from UNAM. Following his PhD, he was a researcher at the Institute of Electrical Research here in Mexico. And since 1996, he's been part of our scientific staff at IMTA in the hydrometeorology department. His research areas are atmospheric dynamics in the tropics, variability and climate change in the tropics, evaluation of Earth system models, dynamical downscaling, and numerical simulation of wind waves. He's a member of the Mexican interinstitutional team that updated the climate change scenarios for Mexico in 2012 and 2017 for the 5th and 6th national communications respectively. And he's also a lecturer in a guided course about tropical meteorology, variability, and climate change. So please, Dr. Salinas, we're looking forward for your talk.
Thank you very much. Can you see my screen? So let's.
Yes.
Okay, thank you very much. So I will talk about models. So there are system models that is included in the CIMIP-6 experiment. Were forced with the new climate change scenarios. In a general way, all the community saw that these models are reproducing in a general way well the general circulation, the global circulation. But in the local and regional aspects, these models are not so well working. So we have to improve this situation for the continent. So as you know, the southern part of Mexico is in the tropical area, and the another one in the extratropical. So this contrast and also the orographic and oceanic influences in the atmospheric processes impact in Mexico. So we have a great diversity of climates and extreme weather. This weather is related to, for example, the migration and the proximity of the intertropical convergence zone to Mexico, but also the North American monsoon that affects in rainfall the northwest part of Mexico and the southwest part of US. Also easterly waves traveling from Africa and the Atlantic Ocean. And in some cases, these easterly waves become hurricanes. And in winter, we have cold fronts. So we have several things that promote this extreme weather. So we evaluated the projections of these models in two variables, temperature and precipitation for 30 years in the historical period, but also for near future and far future. For these futures, we analyzed the simulation for using two extreme scenarios. That is the first one, SSP 5, 8.5, and SSP 1, 2.6. That is the extreme scenarios. So as a background, the CIMIP-6 project were planned to answer three questions. The first one is, how does their system respond to forcing? The second one is, what is the origin and consequences of systematic model biases? That is, if we can see, for example, the model biases could be related to the regional phenomena, but also global phenomena and its relationship. For example, the clouds and circulation is a complex process, and we have to understand better to see if this is a systematic bias, and also the ocean-land contrast. So the bias is not easy to identify and to associate to a process. So the third one is, how can we assess future climate change given climate variability, predictability, and uncertainties? That is, with that uncertainties, we have to evaluate the impacts. So this is not easy, and we have to decide how we can construct the best information for the public in general. So the data that we used are for evaluate the models, the 25 models for the CIMIP-6 were crew data and era interim reanalysis for the historical period. And for the future, we use these two extreme scenarios. So we can compare it for the past, in the historical period, how well the model can reproduce the main processes here in the tropical part. So in a general way, the results we can see in this simplified diagram. The database that we use is the crew observation and era reanalysis, and obviously the 25 models that we wish to evaluate. Using these metrics, root mean square error, mean absolute error, standard deviation, and correlation. And we use just precipitation and mean temperature, surface temperature. We calculated annual cycle and seasonal cycle for four regions, 2 in the north part of Mexico and 2 in the south part of Mexico. So in a general way, we analyze spatial and temporal variability for these models for our region in Mexico. So the precipitation is one of the most difficult issue to simulate by the models. So we have here on the left side the era interim precipitation. So we can see the typical intertropical convergence zone, and there's two extreme precipitation here in the south part of Mexico between Guerrero and Oaxaca states, and also in Chiapas. And also we can see here the monsoon and the middle of the center of the country with less precipitation. With the multimodal ensemble, we can see in a general way the same in the ocean. The ocean is easier to the models to reproduce the precipitation, but in the continents it's not so easy because we have the orographical feature. So in the model are not well represented because of its low resolution. But in a general way, we can see the distribution without the precipitation in the continent. This is in Mexico, but without these extremes that we saw in the era interim data. So in the for the temperature is easier for the models to reproduce that. So we can see in the left side on the panel the temperature. For example, we can see in the tropical Eastern Pacific temperatures less than 22 degrees Celsius. And we can see, for example, here the effect of the mountains here in Mexico with less temperature, less than 20 degrees, because we have, for example, here in Chihuahua, Durango, we have this extreme temperature. And for the multimodal ensemble, we can see in general way the same spatial pattern, even in the continent. So the temperature is better reproduced by the models even for the continents. So we analyze 4 areas, and in the rest of the presentation, I will focus only in the southeast area because we receive every year more precipitation here. So we can see, for example, the CRU and the ERA data in the annual cycle graphic. And so we can identify in a general way a bimodal distribution with 2 peaks, one in with maxima, one in June and the other in September from the historical period. And the multimodal ensemble can reproduce in a general way the 2 peaks, but not the variability between July and August, that is the midsummer drop. And for the future, the near future, for the 25 models, we recognize here a shift of the peak. From the maximum in September could be in October. So this is taking in account the 25 models. I will say something different when we select the best models. So in the top part of the panel, we can see the 25 models. On the left side, we can see the first half of the models, the 12 models. And on the right side, we can see the best models. I will focus on the best models, and we can identify here in a general way the bimodal distribution, comparing with the CRU and ERA interim databases. But not all the models can reproduce this bimodal distribution. So that's why we have to select the best model or the best several models also. So we can identify here the Canadian model and also a French model, the CNRM model. So these 2 models are working better for our region here in the southeast part of Mexico. And the rest of the analysis will focus on this. So for the future, the near future, we can see, for example, here the ensemble of the models. Obviously, we don't have data for the future, but we can see that it still is here the bimodal distribution in June and September. And this here we have our models, the best models, Canadian and French models. And for the near future, we can see more or less less precipitation by 1 millimeter per day, some more or less. But it is not, I mean, we have to take in account in a better way, because the ensemble is not explaining many things. So for the temperature, we can see here, for example, the typical annual cycle for the southeast part of Mexico. We are in the same part. So we can see, for example, from April to September, the maximum that we recognize here our models, our best models, the Canadian and the French model. And for the near future, for the scenario SSP1 2.6, that is not the extreme scenario, we can recognize here more or less the same distribution. And this is we can see here in black solid line, the ensemble of the multimodal ensemble. And for the near future, but the worst scenario, we can see that in a general way, we could have more in 1 degree more that we have right now. But we have, remember please, that we have a seasonal variability. So we cannot only say that we will have more precipitation or temperature just in an annual perspective. We have to see that in a seasonal perspective.
You have 1 minute left.
Yes, thank you. So if we see the comparison between the 25 models with the crude data, we can see that we have correlation between 0.5 and 0.8. But if we see the temperature, the correlation is better, 0.8 to 0.95. So, and we can recognize here our models. So this is our best model, the Canadian model with the least error, mean absolute error. So as a final remark, I can say that we recognize the best models, and using this model, these models describe cycle precipitation in the southeast part, but also in the ocean, the distribution of the temperature of ocean. With these models, we will improve precipitation and surface temperature using dynamical downscaling. So the next year and this year we are working in a program, a project with Canada, the Quebec University and Universidad Veracruzana, to have this dynamical downscaling for 2 regions, in Mexico, in the Veracruz, and also in the southern part of Quebec. So also we submitted a new project to CONACYT. So we are working in that. We will continue to do that dynamical downscaling. So thank you very much.
Thank you very much, Dr. Salinas. And so now this is the end of the first roundtable. We will move now to our first keynote lecture by Professor Jeffrey Neal from the University of Bristol. And I leave you now with Jorge Velázquez so we can continue with the program. It was a pleasure being here today, and see you tomorrow.
Thank you, Agustin. Thank you, everybody, to stay tuned. As we have some time delays, we're going to cut right now the Q&As. But if you have any questions that you want, or you want any information about the speakers that you just that they just passed, you can do it so on the chat. So they can just put the information there, and they can answer some questions. Before going to our keynote speaker, I would like to remind the participants that we were not here at the beginning, some of the dynamics that we are following in this event. As you can see, all the microphones are muted, and they will stay that way, so everybody can have a better experience. So the interaction will be through the chat within the Zoom application, and for our social media attendees, it will be done through the comment section. So if you have any question, if you have any participation you want to do, you can do it. So, and our keynote speakers, our participants, they can answer on the chat. Now, let me introduce to our first keynote speaker, Professor Jeff Neal. He is an associate professor, Turing Fellow, and head of the Hydrology Research Group at the University of Bristol. He's also a founder and chief scientist officer at the university spin-out company Fathom. His research focuses on the simulation and understanding of surface water dynamics in rivers, floodplains, and wetlands, using numerical modeling, remote sensing, and data assimilation methods. He has applied his research to socially relevant problems in fields including flood risk management, flood forecasting, and disaster risk reduction. In recent years, he has focused on large-scale flood hazard and risk assessment and has been at the forefront of developing new numerical methods to simulate floods in data-spare areas to support climate change impact analysis. Professor Neil, thank you and welcome you to this binational conference. I will remind you, you have 30 minutes to give your presentations. 5 minutes before your time runs out, I will give you a sign so you can conclude. Thank you very much again, and the mic is yours.
Thank you very much, Adrian. I hope the slides have come up. Have they appeared? Actually, I can't tell.
Yes, we can see it.
They have, brilliant. Okay, so thank you everyone, and also thank you for inviting me to speak at this conference. I'm very honoured to do so. Today, I'm going to present our work on global flood hazard mapping and how we use that to support climate change impact assessment, so looking at potential impacts of climate on flood hazard. I'm going to get out of the way the main principal disappointment of my talk today in many ways, in that I don't have, or we haven't yet done, our future flood simulations for Mexico. So I'm going to use examples from the UK today. But as I do that, keep in mind that we're using a global flood hazard modelling framework here. So these models can be run in, or we do run them in Mexico, just not the climate change scenarios yet. And what I'm essentially going to do is present you the development of this model, give you a bit of the scientific background on how it works, and then we'll finish up by presenting some of the climate impacts that we get from various future warming scenarios. Also, just to say a big thank you to many of my co-authors who did a lot of the work that I'm going to present today, and of course those who funded it. So in Bristol, in the hydrology group that I'm part of, we develop a global flood hazard model. It looks a bit like this across the continent of Africa. So here we see the 1 in 100-year flood extent simulated across the continent at 90-meter resolution. And what this map is showing is the depth of water we'd expect to be exceeded once in 100 years, according to this model. We also apply the model regionally. So here's an example, the closest example I could find to Mexico in our database. An image of Houston. This is coastal flooding now for present day and future. So all of this is done in the same modelling framework. And I'll take you through how we do that and how we got to that stage. Just by way of additional background, we simulate 3 types of flooding with our model. The first is fluvial flooding. So this is flooding from main rivers where the river bursts its bank and inundates floodplains in a kind of the traditional way that most people think of flooding. But we also simulate pluvial flooding. So this is flooding from intense rainfall, where we get quite localized and short duration flooding from heavy bursts of rain. We also simulate coastal flooding from extreme sea levels, which we, in a climate change scenario, will often add sea level rise to. The modelling that we do uses a hydrodynamic modelling system that essentially simulates the movement of surface water across the land surface in 2 dimensions. This is an example from our UK model for the town of Tewkesbury in the UK. This is the River Severn. What you see in this simulation is initially at the confluence of these 2 rivers here, we see the river pops out of bank, and then we see the flood wave propagate downriver, down towards the southwest here, progressively flooding and then dewatering a little bit. So this is the type of model we use, and the main development that we've been doing is working out ways to apply this model globally, and then to look at how climate might affect the simulations that we produce. That's for the UK. If we look, I can also show you an example of this model applied in Mexico. So here we see the same model, but in this case, we've categorized the outputs. So rather than showing a particular depth, here we've got basically categorized hazard, which is based on the return period of flooding. So we see here areas in blue, areas that are quite unlikely to flood. So we expect rarely to flood. And then going up towards the yellow areas where we would expect flooding to be more regular. So in this case, about 1 in 20, 1 in 30 years. These will often be kind of recognized floodplains by that stage. The low risk areas are those that often have been developed, in this case for agricultural purposes mainly, and where we might expect to see most of the flood risk. So what I'm going to do is tell you a little bit about how we developed this global model, then take you through the evaluation of this model, and then to some climate change assessment. So the global modelling work we do in Bristol really started back in around 2005. As you can see, back in 2005, our plots are all in grayscale. But here we first started looking at simulating large-scale flooding in the Amazon River. So this is a stretch of the Amazon and the Purus River, close to Manaus in Brazil. And this work was simply to take spaceborne data from the Shuttle Radar Topography mission and actually try and simulate the inundation of the Amazon wetland, which is a really, really very extensive wetland either side of this river that floods annually. So in this early work, we had to do a lot of work to remove vegetation from the digital elevation data that we had to try and simulate these floods. And actually, the work was surprisingly successful, to be honest. We were able to simulate essentially the maximum extent of flooding that was being observed each year with a reasonable level of accuracy. However, one thing the model really didn't do was dewater the floodplain in the right way. And what this kind of told us was that these models at the time, whilst they were able to recreate flood extents, they really very much did that for the wrong reason. The reason why places flooded wasn't because of the hydrodynamics or the hydraulics that were really going on, but actually some other kind of overland flooding mechanism that didn't really happen. So around the same time, a lot of colleagues of mine did work on really understanding why these large global rivers inundated their floodplains and how we might better represent those processes in a large-scale flood model. And a lot of this work focused on understanding the role that river channels and particularly floodplain river channels had on the dynamics of flooding in these large rivers. And particularly interesting work by a colleague of mine called Mark Trigg, who's now at the University of Leeds, looked at how the connectivity onto the floodplain of channels in the Amazon River linked up the river to its floodplain and controlled the flood inundation dynamics that we saw. So this got us thinking in particular about then how did we put this into a model that we might be able to apply at large scale in a reasonably parsimonious way that would enable us to simulate large scale inundation in a kind of data sparse area like this. So what we came up with was basically an extension to the model that we already had. We develop a flood inundation model called ListFlood in Bristol. And essentially this is a gridded model. So we lay a grid across the Earth's surface. We give all the grid cells elevations, and then we put water onto that grid and the water flows downhill according to a simplified version of the shallow water equations. So the water moves around and these models work really well at low resolution. But in our kind of larger scale test cases, they were fairly inaccurate. So what we did was basically we added a series of additional parameterizations to our grid cells to account for river channels. So this is a model we call the subgrid model, and we essentially added parameters to our model to describe the bank elevations, the channel widths, and then we made some estimates via various means of the channel depths and the frictions in our model. This gave us a model that we could then apply over quite large areas efficiently to simulate the dynamics of flood inundation. at large scale in a kind of practical way. We did some work on this to then evaluate how well this model then worked on some large-scale test cases. So here we see an example for a large delta system on the Niger River in Africa. So this is the Niger in a delta in Mali. And here we see some observations of seasonal flooding that occur on this floodplain. 7th of November here is during the wet season, when we see a maximum flood extent. It's around a 200-kilometer wide floodplain here being inundated during the wet season, and then in the dry season a complete drying of the floodplain. And unlike ours as an example, where we could wet the floodplain that we couldn't dry it, what we wanted to be able to do here was simulate this wet and dry dynamic with our inundation model to give us some confidence that the model simulated flooding for the right reasons. So then we did a bunch of simulations with our newly developed model, and also with various simplifications of that model that previously existed. We found that we could get better simulations using this subgrid model, particularly of the dynamics that we were seeing on the floodplains. So this was around 2012, and then around 2015, we then decided to take what we'd done here and we started to think about the process of modeling globally the entire world and simulating the flood inundation on that global scale at high resolution. And essentially this boiled down to solving 4 problems. One was a problem of extreme data scarcity. So this essentially means that most rivers around the world are ungauged and they're unsurveyed. So we had to build a model that's essentially based entirely on remotely sensed data or regionalization of data from where it does exist to ungauged locations. We had to solve the problem of flood inundation models being computationally expensive. So we developed various means of running our model quickly on the computer resources we had available. We also had to deal with the problem that floods are extremely shallow waves with very long wavelengths, and so they're sensitive to quite small errors in topography. So we've done an awful lot of work on global scale digital elevation models, and particularly on removing vegetation from those models so that they're suitable for flood inundation simulation. We also had to deal with the fact that some places are much easier to model than others. So it's very easy to validate the model in some places and actually misrepresent the skill that the model had in others. So essentially, we then set about making 5 developments to the model. We put together methods to estimate extreme river discharges globally using a statistical method. We worked out the location and size of global rivers. We dealt with the floodplain topography, and we did the modeling as well. And so that led to in 2015, we published a model that looks a little bit like this. So this is our first global flood model that we produced in Bristol. This was the first model that simulated hydrodynamically flood inundation at 90-meter resolution for the whole Earth surface at a number of return periods. And essentially what this model looks like is that we have extreme flows coming in at the top of the model. And then we have this hydrodynamic model from which you saw the simulation earlier, simulating the floodplain inundation. And from that, we can estimate flood hazard and intersect with, say, population data sets and other things to estimate risk and impact of floods. In the climate change case, what we're typically seeing is that under climate change, we will then change these upstream flows that come into the model, or at the bottom end of the model, we'll change the downstream water levels, which are typically sea level and extreme surge heights out to sea. So how this model fits in with the climate system is that basically the driving forces that go into the model, the forcing terms, can be altered to account for changes to the climate or other scenarios. So we did some validation of this model. And we were surprised, to be honest, that it worked at all. This is our global model applied in the UK. So we're not using, in this case, any UK data in the model. It's just purely the global model that we ran everywhere. And here we see the River Severn catchment in the UK. So the River Severn is the longest river in the UK, has quite extensive floodplains. To the south here is basically Bristol, and we move up to the north past Birmingham, that's around here, and into mid Wales, that's over in this location. And everywhere you see green here is where our global model agreed with the Environment Agency's 1 in 100-year flood map. Everywhere which is blue, our global model's over-predicting, and everywhere which is red is under-predicting. So quite a bit of green here. What this basically amounts to is that on larger rivers, so above 500 kilometers squared, we were getting about 60 to 70% of the floodplains correctly predicted by this global model. If you aggregate to around 1 kilometer, then you get about 5% error rate. So the model had some skill at representing a local benchmark, which in this case was produced by the Environment Agency. Nevertheless, at the time, we were surprised how well this did, but in reality, I think that there were still issues with these models. And one particular analysis that we're involved in looked at comparing then our global flood model with a series of other global flood models. There were 6 in total at the time that this paper was written in 2016. And we did basically an intercomparison of these 6 models over the continent of Africa, and published a paper which is basically entitled The Credibility Challenge for Global Fluvial Flood Risk Analysis. So this was essentially saying, are these models credible? Because each of these models had done various bits of validation work, suggested they were quite successful, in our case saying it was 60 to 70% accurate. What we see then here is the results of this intercomparison over the continent of Africa. So what this basically shows is for every, in this case, 90 by 90 meters square of Africa, whether the models agree that the land surface would flood in the 100-year flood extent. And so everywhere where you see kind of the orange here, that means one model thinks that area would flood. And everywhere where you see 6, or down into the blues here, we've got all 6 models agreeing that area would be at risk of flooding. And the striking thing about these results is that the models disagreed more than they agreed. So if any model were the truth, then the rest must be wrong more than 50% of the time. Interestingly as well, we see areas where the models very much agree, and areas where the models very much didn't agree. And it's particularly, we see this example of on the Niger River here, where the floodplain is quite confined and you've got kind of well-developed, kind of obvious floodplains. The models all pretty much agreed where would flood. And we can say with high confidence in that case that we kind of know where the floodplains are here. When we get onto the deltas, however, we see large amounts of disagreement between the models. This is where the kind of choices you make over the hydrodynamics you simulate really start to matter. So we had a series of models that disagreed a lot, and we felt that there was further work needed to improve these. So we've, over the next 5 years, we've essentially been working on this model to improve the performance of the model relative to a number of benchmarks, and also using new data sets to bring in and improve the accuracy of the model in terms of its representation of floodplains. So here we see that 2050 model I just described on the left-hand side here, called Global Version 1. This is the simulations we predicted. When you look at the floodplains here, you see it's kind of quite blotchy and smooth, and it doesn't really look like what a real floodplain looks like, and you can't necessarily see the rivers or the structure to the data. Our second version of the global flood model, which we released a few years later, we'd done a lot of work on the digital elevation model and how we represented the rivers. And here you can start to see some more structure in the data. We can see the river channels themselves. and we've got deeper flooding near the river channels. It's got some structure. It's not so blotchy anymore. And actually, when we compare to observation data, that's the red here for a flood 2 years ago. Incidentally, sorry, this is Beira in Mozambique, which was hit by Cyclone Idai in 2019. We can see that there's reasonable agreement between these two data sets. Note that this is a particular return period we're simulating here versus a flood event, so we wouldn't expect complete agreement. Also, with the observations, you see lots of gaps in the data. This is vegetation cover. So obviously we can't, the satellite in this case, which is a SAR satellite, can't see through vegetation. But what we do see is that in general, the location of the floodplains is accurately represented by the model. And also that there's been an improvement over time in the model. Since then, we've then further moved to improve the model and moved from 90 to 30 meter resolution and brought in a new data set based on the Copernicus DEM, which is part of the, for those who know things about DEMs, is derived from the TandemX satellite mission. And so these are our latest simulations at 30 meter resolution. In this case, an example from Vietnam. We see now version 2 of the model is this 90 meter model here. On the right, and then version 3 of our model, so the 30 meter model, is here on the left for 2 locations. The interesting thing here is, so in this version 2, we can see the main river conduit, if you like, resolved in the model. By version 3, we're now starting to see things like relic channels on the floodplain and real structure to the floodplain morphology that we've not seen in previous simulations. This is then the latest version of our global flood model, which we're slowly rolling out over the whole world. We've run in a few locations so far, and unfortunately not Mexico yet. So essentially, our contemporary models, we have 3 sets of data that we produce in Bristol. We produce a global flood model, which has this 30 to 90 meter resolution and simulates return periods at 10 different return periods everywhere. We have bespoke models in the UK and US that have a slightly higher resolution, which I'm going to present climate change scenarios for today. And then we also, something that I'm not going to talk about today, but also with an insurance focus on, we have a catastrophe risk model where we generate event sets rather than return periods. If anyone's interested in that, please do drop me a message and I'll happily talk you through those. So if we move on to look at the UK, this is our UK model now. This is that same location in Tewkesbury where we saw the animation earlier. On the left-hand side here, we have the Environment Agency's flood map for the area. On the right-hand side is our global flood model. So keep in mind that this model doesn't use any local information other than the digital elevation model when it's being built. And a regionalization of the river gauging station data that we have in the UK. At the bottom, we see another example of this model being used in a more urbanized setting in Reading. This would be the Thames River along the top here. So this is the model applied to the UK. We can see it in a coastal example as well. Here's just south of Bristol. Bristol is up here. This is the Somerset levels, quite an area that has historically flooded quite often in the UK. Again, we see the agreement between the Environment Agency's flood map and our global flood model. So at this point, you might say, well, why bother running this model? We have data from the Environment Agency on flood extents. Why do we need another data set? Well, the reason for that is that we're then going to, because once we've set this model up, we can run it under different climate scenarios quite easily. We're going to run then the different climate scenarios. Lastly, on this model development in the UK, we also include flood defences. So the UK has a database of flood protection standards and defence height information. This is the city of Exeter. As Albert was presenting earlier from Exeter University, I thought I'd get an Exeter example. Here we see the River Exe running through the centre of the city. And the flood extents, if we ignore the flood defences, And then we can look at the 1 in 100-year flood extents if we include the flood defences in the model, successfully protecting many of the urban areas. Interestingly, we can also, because this is a hydrodynamic model, we can see the impact the flood defences have on inundation upstream. So if you look carefully at this area where I'm circling with my mouse at the top of the city, at the north end of the city, you can just about see that when we don't have the flood defences in place, the water depths just up here are a little bit shallower than when we do. And this is essentially the space that's being made being taken up for the water by the flood defences is forcing that water to inundate the floodplain a little bit deeper upstream, and also downstream there's some more additional flood depth as well. So things you might expect from this type of model.
5 minutes, please.
Thank you. So lastly, I'm just going to talk for the last 5 minutes about the actual climate change scenarios that we've run. So for the UK, we've run 3 climate change scenarios, RCP 2.6, 4.5 and 8.5 out to 2070. Here you can see the changing extreme rainfalls for these for RCP 8.5. We've also had sea level rise scenarios to go with these as well, using data from UK climate projections 2018. So here, now looking at an example from Bristol, this is Avonmouth, present day and 2070 under RCP 8.5. The flood extents that we'd expect for the 10-year and the 100-year flood extents, what we really see is a big growth in the low return period flood extents, which areas we wouldn't want to flood this regularly. And we can pull out kind of national scale analysis from these kind of data. So this is present day flood risk in the UK. So this is number of properties with more than 1% chance of flooding in any given year. So properties within the 1 in 100-year floodplain across the UK. And what we can then look at is the percentage of properties in 2050. So we can see the growth in properties that are within this floodplain out in 2050, in this case under RCP 8.5. And we can look at the change in that as well. So we can see which regions of the country are likely to experience the most change in risk over this time. We particularly see South Wales as a hotspot, and some places in London. This includes pluvial and fluvial and coastal flooding in this analysis, which is why the spatial pattern is quite complex, and also the flood defences are quite complex as well. So that's the story from the UK. Just to finish up, I'm going to go a little bit north of the border from Mexico into the US and give some examples just to finish up from conterminous US. So here's Houston again, the 1 in 100-year coastal flood extent for present day and future. This will mainly be based on hurricane storm surge, of course, with the addition of sea level rise in the future and perhaps some intensification of those hurricanes. And we can finish up by looking at the distribution of risk across the US that we get from this type of model. So this is the number of properties, again, at risk of more than 1% chance of flooding per year. Where FEMA have data, there's about a 70 to 80% agreement between our model and what FEMA think. FEMA doesn't cover the whole of the US, so our model fills in the gaps. We see some very high levels of risk, particularly around the Gulf Coast and in Florida, over 200,000 properties in some cases at risk of more than 1% chance of flooding per year. And when we apply the climate scenarios, in this case RCP 4.5, actually we can see some quite dramatic increases in risk, particularly along the Gulf Coast of the US and up the eastern seaboard. An 18% rise by 2050 in the number of properties in this 1% per year risk category for Florida, and locally some very large increases in the percentage of properties at risk. So I hope that was interesting, and we would like to extend this work to include Mexico and the rest of the world in the coming year. So just a summary, we've been working on global flood modelling. There's some skill and it works. there's been significant recent improvements, but we still have a limited understanding of uncertainties and lots of work still to do on the climate sensitivity analysis to see into the future what risk might be doing due to climate change. So I hope that's been interesting, and thank you for all your time and patience. And I'll finish up there just ahead of time, and hope everyone has a good day and a good evening. Thank you.
Thank you very much, Professor Neil. Yeah, you just go on time. You just finish on time.
Thank you.
Thank you very much for that. As we are a little bit delayed on our program, if you have any Q&A for our Professor Neil, please do it so on the chat on Zoom, or if you are in social media, do it in the comment section, and we will bring it to Zoom so Professor Neil can see. And if it's not much of a problem, Professor Neil, you can maybe share some or answer some of the questions, like if someone put it on the chat.
Very happy to. Thanks.
Thank you very much again for this interesting presentation to show us that global modeling is possible and is a reality now. Thank you very much. We're moving on now. We're going to cut the break so we can go on time. We're going to our expert roundtable 2 on the topic climate change and weather extremes. In this expert roundtable, our friend Fernando Gutierrez Champion is going to be the moderator. So I'm just going to give the mic to him. Thank you, Fernando, to be here, and it's all yours.
Thank you, Jorge, and hello and welcome to the second expert roundtable on climate change and weather extremes of the first binational conference on climate change, water, agriculture, and economics, organized by the Mexican Embassy and the Mexican Institute for Water Technologies, IMTA, in Mexico. I am Counselor Dr. Fernando Champion from the Mexican Embassy, and it is an absolute pleasure to welcome our next 4 panelists who will be discussing how extreme weather events are reshaping the world we live in. The World Meteorological Organization's State of the Climate Report 2021 highlights a world that is changing before our eyes. The 20-year temperature average from 2002 is on course to exceed 1 degree Celsius above pre-industrial levels for the first time. And global sea levels rose to a new high in 2021, according to this study. This year alone, we saw how it rained rather than snowed for the first time on record at the peak of the Greenland ice sheet. We also saw a heat wave in Canada and adjacent parts of the US pushed temperatures to nearly 50 degrees Celsius in a village near British Columbia. Death Valley, California, reached 54.4 degrees Celsius during one of multiple wave-ins in the southwestern US. Months' worth of rainfall fell in the space of hours in areas of China, while parts of Europe saw severe flooding, leading dozens of casualties and billions in economic losses. And a second successive year of drought in subtropical South America reduced the flow of river basins and hit agriculture, transport, and energy production. Now, to give us further insights about how extreme events are the new normal, I'd like to welcome Professor Razieh Fermani from University of Exeter, Dr. Arthur Mann-Yuelan from Cardiff University, Dr. Christian Appendini from the Institute of Engineering, UNAM, and Dr. Guillermo Murray Tortarolo from Institute of Ecosystems and Sustainability Research, UNAM. Professor Fermani is Associate Professor of Water Engineering and Industrial Fellow of Royal Academy of Engineering at Center for Water Systems, University of Exeter. She is the chair of IWA's Intermittent Water Supply Specialist Group, and she specializes in urban water systems modeling, water resources management, and asset management, and has expertise in multi-objective optimization of water networks. Her research interests cover evolutionary optimization, artificial intelligence and data mining, and their applications in real-time control for water systems, asset management of water distribution systems, leakage, pressure and energy management, reliability, resilience, and sustainability, asset failure and deterioration modeling, and intermittent water supply systems. Thank you, Professor, and the floor is yours.
Thank you very much for your introduction. I'm going to share my screen. Good morning, good afternoon. My talk is slightly different. I'm going to talk about research activities at the Center for Water Systems on intermittent water supply systems. Intermittent water supply systems, when customers have got a piped network at the household level, but they don't receive water 24 hours a day or 7 days a week. And this can be in different shapes. For example, they may have a permanent intermittent supply system that is throughout the year. But in some cases, we may have seasonal intermittent water supply systems. And in some places, because of intermittent supply, customers end up installing their own storage tanks. And when they have got access to water, they store the water and use throughout the day continuously. Why it is important, as we can see in this figure, around 18% of population have got intermittent access to supply. That means 1.3 billion people throughout the world. And it is interesting to hear that it's not only in regions with very dry weather. We have got a lot of cases in Europe as well. For example, in Cyprus, in Italy, in Spain, there are cases that customers don't have access to water 24 hours a day. And what are the reasons? Global climate change, not having enough resources, population growth, and also urbanization, putting huge pressure on existing infrastructures, and then they end up converting them to intermittent water supply systems. We have developed this framework that shows a management framework, how to manage these systems. So starting with causes, threats to these systems, population growth, climate change, urbanization, aging assets. And this is resulting in decreased supply while we have got increased demand. And at the same time, assets are failing. So we have got huge leakage in these type of systems. And these are resulting in intermittent supply of water, or some utilities, because they have got population growth, they are expanding the system beyond its capacity. And from customer point of view, they are ending up investing in tanks and pumps to adapt to these changes in the system. And the consequences are inequity in the system, increased leakage, health-related problems, less willingness from customers to pay, assets are deteriorating in inefficient operation, and wastage of water. As part of this framework, we have also identified measures that, for example, at this stage, how to mitigate the impact of these changes, how to adapt to these changes, how to cope when things are changing, and finally, how to learn and improve our management. So at Exeter, we have got a number of researchers working on intermittent water supply systems. The focus is not on the water resource. So if we have limited water resources, obviously there should be a lot of work on how to make more available water, looking at alternative water sources. The focus is mainly on management, current research that we are doing. So if we have limited sources or we have sufficient sources, how to better manage these systems to make sure that we have got equity among the customers and we reduce leakage, wastage, etc. So we are focusing on operational measures, how to better manage pressure, demand, leakage, and also capital investment, how to do asset management to make sure we are going to have sustainable, resilient systems which provides equity among their customers. So we are doing a lot of work on modeling. Current existing models for continuous water distribution systems are not suitable for intermittent water supply systems. These systems, they have got their own characteristics, and we can't just use existing methodologies, tools to capture the real characteristics of these systems. So we are doing a lot of work, laboratory experimental work, field measurements, as well as studying uncertainties related to user behavior and utility behavior, how they are governing these systems, and trying to develop models that better represent these systems. And using those enhanced models, we are trying to introduce some interventions to guide the changes in intermittent water supply systems and eventually contribute to transition from intermittent to continuous water supply systems. Currently, we have got several PhD students. They are working on different aspects of this modeling. The reason that existing hydraulic models are not suitable for these systems because the existing models mainly work on pressurized systems. The assumption is that the pipes system is fully pressurized. However, in intermittent water supply system, we have got filling process, pressurized state, and also emptying phase of the system that can have big impact on the equity on the customers. Another big factor in changes in the hydraulic models are these tanks that customers have got tanks and they fill their tank and their behavior is not very clear. So they leave taps open because they are not sure when water is going to arrive. So we are expanding the existing tools, IPANET and IPASWIM, and further developing those to make sure that they can better capture these characteristics of intermittent water supply systems. Also, we are doing a lot of activities on uncertainty quantification, improvement of equity indicators, as well as sectorization of these systems to make sure we can better manage them. Especially these systems are prone to leakage. In some cases, we could have 60-70% leakage. To improve, reduce leakage, improve efficiency. We are working in different case studies. Currently, we have got case study in Zambia, looking at leakage management and also transition from intermittent to continuous systems. We are looking at another case study in Zimbabwe, looking at demand uncertainty, impact on equity. Another case study we have got in Palestine. So some of the factors influencing the intermittencies are not water related. For example, in this case, there is a major problem with energy intermittency, which is resulting in the water intermittency. So we are trying to see how we can better operate our pumping station in order to reduce the intermittency. And just 2 weeks ago, we submitted a research proposal to European Commission, and we are going to work on it. If it's successful, there is a case study in Mexico City. We are going to look at the, if I pronounce it correctly, is Taplapa region of Mexico City. And the idea is to explore to see how we can reduce the leakage, improve the efficiency of these systems. And this is my email address. Thank you very much. If you are interested in the topic, please feel free to contact me.
Thank you very much, Professor Farmani, for your splendid presentation on intermittent water supply systems. And we'll have a short segment at the end of this panel to present questions from our audience. Next, Dr. Man Yuelam will provide insights on water quality prediction framework for energy efficiency improvement in wastewater treatment processes. Dr. Mann graduated as a civil engineer and researcher and have participated in research in water quality modeling, flood mitigation, transient effect detection in water supply systems, and hydrodynamic stability theories. His current research involves mechanistic and artificial intelligence models for sustainable development and public information concerning water quality. Thank you, Dr.
Okay, thank you. Can you see my screen? Seriously, can you see my screen?
Yes. Yes, we can.